In this video we'll look at the derivation of the fundamental theorem of calculus. So we have the area under the curve between x equals a, x equals b, and this is our notation for the area. So our limits are from a to b, and the area is expressed as capital A to b if we're working between a and b. So down here, the area there is area T, so therefore we start at A and finish at T, so there's our lower limit and our upper limit. So if we were to focus on a narrow strip in that region between x equals T and x equals T plus H, to work out the area of that strip we would subtract a small area from a large area. So if we were to calculate first up area T, once again that is between A and T, and then the area between A and T plus H would be area T plus H. So subtracting those two areas from each other would leave us with that narrow strip. So our expression for the area of the strip is AT plus H minus AT. Now if we look at an enlarged version of that strip there, we have lower and upper rectangles either side of the area we're after. So the area we're after is this expression here. That will be less than or equal to the area of the larger rectangle, and it will be greater than or equal to the area of the lower rectangle. Now to find the area of the rectangles themselves, we have width times height. The width is h and the height is this y coordinate here, which is f of t. And the area of the upper rectangle, once again, the width is h, and the height of that rectangle is the y coordinate here, which is f of t plus h. Now if we divide all sides by h, we end up with f of t, and in the middle here, that expression will be divided by h, and the right hand side term, the h will cancel out. Now if we consider the strip getting narrower and narrower, h approaching 0, then if you look at that middle term there, that is familiar, that is from the first principles, and as h approaches 0, that becomes a dash of t. Now as h approaches 0 for the first expression, f of t, it makes no difference. But as h approaches 0 for this term here, then the h becomes smaller, we're left with f of t. Now if a dash of t is greater than or less than f of t, then it in fact is equal to f of t. So a dash of t, the derivative of the area, is equal to little f of t. So working backwards from those derivatives, a dash of t takes us back to a of t, the original function, the area, and little f of t, recall, is the derivative of big F of t. So working backwards, we'll write big F of t. And recall also that when we differentiate, we lose a constant. So these two terms are equal to each other, but the constant may have disappeared, so we write a plus c. Now consider what happens when t is equal to a. So what is a of a equal to? That's the area between x equals a, which is 0. So if we let t equal a in our equation here, we have a of a is equal to f of a plus c. And if we substitute a of a as 0, we can then rearrange, make c the subject, So C equals negative f of A, which we can now put into this equation here, replacing C. So A of t is equal to f of t minus f of A. Now, we are after the area between x equals A and x equals B. So recall that that is in fact A of B. So let's replace t by B. So A of B equals f of B minus f of A. And what is A of B? That is in fact the area between A and B, which is written as the integral, or definite integral, of little f of x with respect to x. So that equation there is our fundamental theorem of calculus, which is what we would use to work out the definite integral exactly.